Welcome to Tutorial 3. Over the next 3 tutorials, we'll explore processes associated with the atmospheric, oceanic, and terrestrial components of Earth's climate system. In this tutorial, we'll start out with atmospheric processes. The figure on the left is showing profiles of pressure and temperature of Earth's atmosphere. The pressure is shown in the dashed line and the temperature is shown in the solid black line. As you can see, pressure decreases higher in the atmosphere. However, the temperature changes are a bit more complicated and are defined by distinct layers in Earth's atmosphere. Most of the atmospheric climate processes occur in the troposphere, so we'll primarily focus on this part of the atmosphere. In the troposphere, temperature decreases with increasing altitude, and this change in temperature with increasing altitude is known as the lapse rate. The average tropospheric lapse rate on Earth is about negative 6.5 degrees Celsius per kilometer. This means that for every 1 kilometer increase in altitude, the temperature decreases by about 6.5 degrees. These vertical temperature and pressure gradients in the troposphere, as well as the latitudinal differences in global temperature that we discussed in the previous tutorial, both contribute to large-scale movement of air masses on Earth. One of the main atmospheric circulation processes on Earth is Hadley circulation, or Hadley cells. This is a large-scale air circulation pattern driven by atmospheric pressure and temperature gradients. Warm air in the tropics rises to higher levels of the atmosphere, and as this air rises, it cools. The air then moves poleward and descends at about 30 degrees north and 30 degrees south. During this time, it begins to cool further, and as it sinks back to the surface, it starts to warm. The air then moves back towards the equator and creates a cell of circulating air masses. And these air circulation cells continue poleward. As you can see in this map, there are 3 of these large-scale air circulation cells in each of the hemispheres. One of the forces that contributes to this large-scale atmospheric circulation, as well as other large-scale climate processes, is the Coriolis effect. The Coriolis effect is a pattern of deflection caused by Earth's rotation. This effect causes circulating air to deflect to the right in the northern hemisphere and to the left in the southern hemisphere. The Coriolis force influences many large-scale circulation patterns on Earth, including Hadley cells, which we just discussed, as well as trade winds. Trade winds are winds that blow east to west just north of and south of the equator. Notice how in the figure they're deflected to the right in the northern hemisphere and to the left in the southern hemisphere. This is due to the Coriolis effect. And remember this figure from the previous tutorial? Well, these large-scale atmospheric processes, such as the Hadley cells and the trade winds, help to transport some of that heat in the tropics towards the poles. In this tutorial, we'll explore global atmospheric temperature and pressure data that's stored as a netcdf file. We'll learn how to use Xarray to import this netcdf file, and we'll explore tools for analyzing and plotting this data in Xarray to produce vertical profiles such as shown on the left and maps such as shown on the right. This can help us to understand changes in temperature and pressure at different levels of the atmosphere.